Boom! Yes folks, Hume again. In this video we're going to continue with our series on Pythagoras Theorem. In this video we're going to just do a couple simple examples just to illuminate the working of Pythagoras Theorem. Alright, we're going to use some simple integer values in the first instance. Then we'll do some values that are not integers, and then in our next follow-up video we will do something else which we will get to when we get there. Good? So just to recap, we know that Pythagoras theorem says that the square of the hypotenuse, right, is equal to the sum of the squares of the other two sides. So in other words, the square of the hypotenuse is equal to the square of side 1 plus the square of side 2. Whatever we choose to call these two sides. We use a particular notation, good, hypotenuse, opposite, and adjacent, to bring Pythagoras theorem and the trigonometry together. But we will get to the trigonometry later. Good? So we're going to just start by doing a simple example. So let us say, for the sake of argument, that we have a right angle triangle whose hypotenuse is unknown. So we don't know the length of the hypotenuse, but we know that this side is 3 and this side is 4. 3 centimeters, 3 meters, 4 kilometers, 4 furlongs, whatever unit you're measuring in. One is 3 and one is 4. And we want to find the length of the hypotenuse. So we know the formula. The formula says that the hypotenuse squared is equal to, in this case it would be 3 squared plus 4 squared. So that 8 squared will be equal to 9 plus 16. 3 squared is 9, 4 squared is 16. So 8 squared is equal to 25, which means then that h is equal to the square root of 25, which is equal to 5. So if we have a right angle triangle where one side is 3 and the other side is 4, we use Pythagoras theorem and we get that the hypotenuse is equal to 5. Now we could flip the script. If instead of these two sides, let's say for example we have these two sides. So in other words, in this case, we know the length of the hypotenuse is 5, but let us, for the sake of argument, say that we didn't know what this side was. No problem. Same algebra, more or less. So this case, we could name the side, right? If we choose to put the reference angle here, just for the sake of having a point of reference, then this would then be the opposite side. So in other words, we have the hypotenuse 5, the adjacent side 3, and the opposite side O, not to be confused with 0. Good, so I'm taking the risk here of doing this, but explaining that this is not 0, this is O. Good, so again, by Pythagoras theorem, this time we have the hypotenuse 5. So 5 squared is equal to 3 squared, which in this case is the adjacent, plus O squared. O is the side whose length we're trying to find. That is the opposite side. So 5 squared is still 25, 3 squared is still 9, and O squared is just O squared. So you bring the 9 across, and that will now become minus 9. So 25 minus 9 is equal to O squared. So in other words, now 16 is equal to O squared. So if your O squared is equal to 16, then your O, which is the opposite side, is equal to the square root of 16, which is equal to 4 in whatever units that you measure. Good. So the algebra is the same. In other words, yes, you're always starting off from Pythagoras theorem, and depending on which side you're looking for, it will either just be a straight addition if you're trying to find the length of the hypotenuse, or if you're trying to find the length of the opposite side or the adjacent side, there will be some subtraction in there as well. So let us do the other permutation now. If instead of 5 and 3, we had 5 and, sorry, wrong color. We had 5 and 4. Alright, let us say, for the sake of argument, that we had 5 and 4 there. Alright, in this case, the missing side is the adjacent side. This is the side whose length we're trying to find, and we go through the same procedure that we just employed to find the length of the opposite side. So again, we start from the essential formula, which is that the square of the hypotenuse is equal to, in this case it will be a squared plus 4 squared. It doesn't really matter which one you put first, right? So in this case it will be 4 squared plus a squared. Good. So the 4 squared, 25, will be equal to 16 plus a squared. 25 minus 16 is equal to 9. Sorry. 25 minus 16 is equal to a squared, which is to say then that 9 is equal to a squared. So if your a squared is equal to 9, then your a is equal to the square root of 9, which is equal to 3, and we get back the 3 that we had there originally. So, and this is something that kind of gets a lot of students, because if they're in a situation where they have to find the hypotenuse, it's not a problem. So for example, if we go back to the very first situation where we had the 3 here, the 4 there, and we didn't know what h was. If they're in this situation, yeah, no problem. Straight addition, and you find the square root at the end. If, however, we flip the script and we say 5 squared is equal to opposite squared plus 4 squared, plus the opposite is 4, plus 3 squared, sorry, right? If we do this, right? So if we do that, suddenly there's a problem, right? Because you now have to deal with the extra complication of having to carry something across on the equal side. In other words, over here, you don't have to deal with anything moving across the equal sign. This is just a straightforward h squared equal 9 plus 16, and if h squared is 25, then h is the square root of 25, which is 5. Boom, no problem at all. But over here, it is not as straightforward, because you have 25 is equal to o squared plus 9. But to find o, you have to isolate o on one side, which means that, what madness is this? Which means that you have to take the 9 from this side of the equal sign and bring it across here. And that is where you get a little thingy. Because if you forget, for example, that in taking the 9 across you have to change the sign, then everything will just go haywire. So if you do this, if you're saying 25 is equal to o squared plus 9, and then you do this, 25 plus 9 is equal to o squared, forgetting that when you take the plus 9 to bring it across here, it now becomes minus 9, then you see where some mistakes could be made. Good. So that is one area where students need to be extra vigilant, right? Anytime you have to find the length of any side apart from the hypotenuse, there will be some subtraction involved. You'll have to take one square and carry it across to meet the hypotenuse on the other side of the equation, and then you run it from there. Good. So again, just by way of example, we flip the script and we have the 4 here, and this is the adjacent. So again, if we had 5 squared, hypotenuse is equal to opposite 4 squared plus adjacent squared. Good. We have to take the 4 squared and carry it across. So we'll have 25 is equal to 16 plus a squared. So your 25, again, when you take the plus 16, remember the plus is understood, you take the plus 16 and then carry it across here. What you don't want to do is that. You don't want to do this. Remember, of course, that when you take plus 16 across, it now becomes minus 16. 25 minus 16 is equal to a squared. So 9 is equal to a squared. A is equal to the square root of 9, which is equal to 3. Good. So what I would have just done is illustrate the basics of finding the length of any side of a right angle triangle if you have the length of the other two sides. Good. Now the procedure is the same. It is just that most right angle triangles you will meet in any maths paper or perhaps anywhere in life will involve decimals. Right? Will involve the use of decimals. However, we have a particular class of right angle triangles which we will deal with in the next video. The next video? No, in the last video in the series, right? I want to deal with a couple examples with the decimals just so that you could see it for yourself. So in the next video, we'll do an example where we're dealing with decimals now, where everything not so integer-ish, right? Same procedure, but we're using decimals instead of whole numbers. And then in the final video, we'll come to a special class of right angle triangles, but we don't want to give it away too soon. Good. So as always, we hope that this video has been educational. We hope that you have learned something, and we hope that you will stick around because we have plenty more to share.